for this one, this is 3D. We're looking at something that's a little different. We're looking at 3 to the n. That is my definition of the members of my group. But n is what we're using to create 3 to the n. So we're not looking at n specifically. We're looking at what happens to 3 to the n. And then we're multiplying values together. We're multiplying two things together. So for closure, what they're going to look at for m and n, element of the integers, 3 to the m times 3 to the n is going to be 3 to the what? This is what Andrew was talking about. 3 to the what? 3 to the m plus n. Yeah. Now what's great about that? M plus n has to be an element of what? If m and n are integers, m plus n are an element of the integers too. Therefore, 3 to the m times 3 to the n is closed. Because 3 to the m is an integer, 3 to the n is an integer, and 3 to the m plus n has to be an integer as well. There we did it. Closure. Closed. How about associativity? For associativity, what we're going to do is we're going to take 3. Let a, b, c be elements of the integers. Okay? And what we're going to do is we're going to take 3 to the a times 3 to the b times 3 to the c. And we're going to try to get it equal to 3 to the a times 3 to the b times 3 to the c this way. Well, what is 3 to the a times 3 to the b? What's the way to show that? A plus b. Good. Times 3 to the c. And then this will be 3 to the a times 3 to the b plus c. Good. So this we can also combine into 3 to the a plus b plus c, and we're going to have 3 to the a plus b plus c here. Therefore, what does this mean? Yep, associative. And for all a, b, c element of the integers. Good. So we got that one done. Fantastic. Now the identity is the one that we were kind of questioning. This one, if we go 3 to the something is equal to, see, they went 3 to the 0. Yeah. So here's what we do here. 3 to the n times t is going to be equal to 3 to the n, correct? So what is this going to have to be? Yeah, this is going to have to be e is equal to 3 to the n over 3 to the n, which is 3 to the n minus n, which is 3 to the 0, which we know and love as 1. There you go. So what is 3 to the n equal to be the identity? What is the identity? Therefore, what is identity? 1 is not 0. What's that? Yeah. 1 is identity for any multiplication, yeah. And then the next thing that we're going to do is we're going to take a peek at 3 to the n. I thought this was kind of interesting. 3 to the n times x is equal to 1. So 3 to the, we'll go x is equal to 1 over 3 to the n. What's another way of writing that? 3 to the what? Negative n. And tell me about this 3 to the negative n. Is 3 to the, where, is negative n still an integer? Yes, element of the integers. Did we say positive integers? No, we just said integers. So therefore, this is still okay. Are we saying that 3 to the negative n or 3 to the n has to be an integer? No, we're just looking at n. So we can say, therefore, inverse exists, and A inverse equals 3 to the negative n. You actually have it defined. So therefore, G operating on star is a group. Ha! Everybody have that written down? Write down as much of this as you can for your notes. Then turn to your neighbor, tell them how you're going to prove abelian. Either one is fine. I like what you said. I like the multiplication one better. All right, let's do commutative real quick. So if A and B are elements of the integers, and 3 to the A times 3 to the B, what's that equal to? 3 to the A plus B? Is that equal to 3 to the B plus A? Yep. Is that equal to 3 to the B times 3 to the A? Therefore, commutative. And group is abelian. Which we kind of expected anytime you have this. You probably would look at this one and say, I would never, ever want to do this one. It looks so horrible. Doesn't it look horrible? But this one is going to excite you to the core because it does something really cool once you get the Cayley table. In fact, the Cayley table is going to be what makes this really interesting. Let's go back in time a little bit. Do you remember the cis form of this? Cis, C-I-S theta? You remember that? Well, yeah, this would be where theta is 0 and r is 1. So this is just going to be 1 cis 0. The next one, now I'm going to draw a picture here. This is going to be down a half, or no, to the left a half, and up square root of 3 over 2. This is going to be an angle of 2 pi over 3, right? So this is going to be cis 2 pi over 3. Would you write that down, please? You're going to love this. This next one is down here, still over negative half, but we're going down this time. You're going down this time, cis. So this is going to be 4 pi over 3, or negative. I like it. But I'm going to go with 4 pi. Cis 4 pi over 3. And just a quick reminder, what's 1/2 squared plus square root of 3 over 2 squared? What is this squared? 1/4. What is this squared? 1/4 plus 3/4 is 1. So that's my radius is 1. Okay. Now, way back when, something cool happened when you looked at cis 2 pi over 3 and you squared it. It's not called de chartreuse. It's called de what? De Mauve, that's right. That was my hint. That was late. All right, so cis 2 pi over 3 squared, what is this going to be? Yeah, so what I'm going to do is, since this is just 2 pi over 3 squared, I'm going to call this 1, which it is. I'm going to call this one z, and I'm going to call this one z what? Z squared. Would you write those in, please? And you can do it here as well. So we have 1 z and z squared. Okay, so what we're looking at here is a relationship of these three. This I'm going to call cis 0 or 1. This is going to be cis 2 pi over 3 or just z. And this one's going to be, they called it alpha, but I don't like it because it sounds like an angle. These are actual values, z squared. This is z squared.
Yeah, I get that. But can you prove again that it is z squared?
This one? De Moivre's theorem. Okay. So tell me what 1 times 1 is. Very good. That's a sharp group. And then the next one, 1 times z is z, and 1 times z squared is z squared. No problem there. Z times 1 is z, and z squared times 1 is z squared. No problem there. By the way, what's the identity of this just by looking at it? 1, yep. Now, z times z is z squared. But what's z times z, z times z squared? That's z cubed. Okay? Now, let's go back. This was cis 2 pi over 3 to the first, and I'm going to take a z squared times z, and I'm going to make this to the third. Use de Moivre's theorem, what do you get? Cis 2 pi. What's cis 2 pi the same as? Cis 0. So this is 1. And this one is 1. And the only one we have to figure out is what is this going to be to the fourth? I'm going to give you a hint. It's cis 2 pi over 3 to the third times cis 2 pi over 3. What's that going to be? Z cubed is 1. This is going to be z. Now, as you're looking, there you go, easy. So when you're looking at this Cayley table, what do you notice about it? It's a Latin square. It is closed. What do you notice is the identity again? 1. 1 is identity because these pair, I like to describe it this way. It's 1 if this pair is the same and this pair is the same. Okay? Tell me about the inverses. Yes, 1 is an inverse of itself. Anything else? Yes. So the only one that's an inverse of itself, we found 1 is the identity. We found the inverse is 1 is, and I want you to write this down, 1 is an inverse of itself. Okay? And what can you say about z squared and z? These are inverses of each other. I don't know. If you find one, let me know. It's closed because all elements exist on each row and column of table. What about associative? Multiplication is associative. Or 3 times 3 times 3, you could do 27 checks if you want. We'll leave that up to Vishal. He'll take care of that for us. He'll do that. How about commutative? Can you look at this and tell me if it's commutative? How? Look at the diagonal. Here's the diagonal. What do you notice about They're symmetrical about diagonal. So what you would do for the commutative is you would say group is abelian because, and take the time to write this, please. Group is abelian because elements on table are symmetrical about the what? Good. And we could also say that since it has these four, it's what? Since group is closed and associative identity. Don't like writing on their faces. I feel bad. And inverse. It is a group. Ta-da!